Our first lesson for vectors is, well, appropriately titled An Introduction to Vectors. So in math and in physics, we usually look at two specific quantities a lot. One that you're used to, right? Such as, say, volume, right? Liters or meters cubed, right? Mass, kilograms, pounds, time, seconds, right? These are called scalar quantities. They just have a magnitude associated with them. When I say magnitude, I mean like size, right? Like 100 kilograms or 5 liters, right? That number tells you how big it is. However, there is another quantity called a vector quantity. Now, vector quantities have a size as well, but they also have a direction. For example, velocity. You could be going 100 kilometers per hour north on the highway. So you see how I added north to it? That's an important component. And so vectors, when we draw a vector, we represent it as an arrow here. Notice this arrow has both a length. That length is associated with its magnitude or size, and it also has a direction, which is associated with its, well, direction. Okay. If we're to write a vector, we use this notation here. I'll just write it big. So if you have some sort of line and you want to indicate it's a vector, you just put an arrow on top of it. If you just want to talk about the vector's magnitude, then you put absolute values around it. So this here says the magnitude of the vector AB. Now we can put vectors on a coordinate system as well. Okay, so if I just zoom in here a little bit, right, you can see here you have the point 2, 0. And we just draw a line from the origin to the point 2, 0, and we represent that as a vector. If you wanted to talk about the magnitude of that vector, well, you're talking about its length. And in this case, the length would be 2. Right there. You can also look at the point -2, 0. Right? And so how are these two vectors related, this green one and that red one? They're actually called opposite vectors. So if you have these two vectors, I'll just make them look bigger. You don't have to call it AB. You can give it a name such as V. Okay. Indicates a vector with an arrow. And then if you take the exact same vector but in the opposite direction, so same size but opposite direction, then it becomes a negative vector. Okay, so this would be V and this would be negative V. For any two vectors to be equal, you would need to have the same length and the same direction. They don't have to be in the same location on a coordinate grid. And if I went back up to this coordinate grid, I can draw one vector from the origin going like this, and another vector somewhere else going in the same direction with the same length. I've just translated the vector. I haven't changed its magnitude. I haven't changed its direction. So it's the same vector. They're equal vectors. So if we were to look at this rhombus here, and here we have a vector, AB. So that is right here. Right? So there's AB. And if we were to look for an equal vector to AB somewhere on the rhombus, you'd see that DC works pretty well. So those two vectors would be equal vectors. All right, so let's look at the first example. First example says, for each of the following, state whether the quantity is a scalar or a vector, and give a brief explanation. So for example, I'll go over a couple. Height. Well, for example, my height is 185 centimeters. I don't know if most of you know what your height is in metric, but yes, my height is 185 centimeters. That doesn't have any direction associated with it. So height would be a scalar quantity. How about mass? For example, this textbook weighs 1 kilogram. Technically, I shouldn't say weigh, but I'm not going to be picky in math class like I am in physics class. But the mass of this textbook is 1 kilogram. Again, no direction associated with that, so it's a scalar. Okay. However, weight is the force of gravity that the Earth pulls down on you. Notice I said down. That's a direction. And so that would be a vector quantity. Okay. Similar over here, force. If I were to push on something, let's say I pushed on a car that was, I don't know, stalled on the road, and so I pushed it down the road in a northern direction. That's a direction, so that's a vector quantity. Okay, so let's go over the rest of these together. We're going to go to example 2. So example 2, it says use a scale where 1 centimeter represents 10 kilometers per hour and draw the following vectors. So the first one is a bicyclist heading north at 40 kilometers per hour. Okay, I'm going to do this on the side here. So if we have 1 centimeter representing 10 kilometers per hour, and let's make a little compass where this will be north, and we want to draw something 40 kilometers per hour north. So let's take our ruler because we want to be specific. And if 1 centimeter is 10 kilometers, then 40 kilometers would be 4 centimeters. So I'll just place this here and draw a vector that's 4 centimeters pointing north, like that. So that would be our vector. Again, all I'm trying to indicate here is that the length represents the magnitude and the arrow represents the direction. So this would be our 40 kilometers per hour north. And usually the direction we write in square brackets. Now the next vector is a car heading in a southwesterly direction at 60 kilometers per hour. So that's going to need to be 6 centimeters. We're going to need to rotate our ruler here. Southwest, well, this would be south, and that would be west. So it doesn't say specifically where in this quadrant, so we're just going to go in the middle, like 45 degrees in that quadrant. And it's going to need to be 6 centimeters. So we'll start it here. And end there. So there's our vector, 60 kilometers per hour in some southwestern direction. So the last example says we have a vector AB, and it's a vector whose tail is at -4 and 2. So let's draw a coordinate system here. Here and here. And let's say each division on this grid is just 1. So -4 and 2 would put us 1, 2, 3, 4, and 2 up here. So there's -4 and 2. There's our point, -4 and 2. And whose head is at -1 and 3. So -1 and 3, right there. So drawing it, we get this. Right? From our tail over here to our head over here. Now part A says calculate the magnitude of AB. So it's a little different from when we had the example that it was just 0 and 2. We can just say the magnitude was 2. But this one goes from here and here. So we can say this length here would be the difference between those numbers, which would be 3. And this length here would be the difference between these numbers, which would be 1. So if we wanted to find the magnitude, and I can write it out nice and properly here. Still messy though, because my writing looks terrible on this pen. We'll write the magnitude of vector AB put a little vector sign there, would equal, now since we're doing Pythagorean theorem, to solve this, because that would be a right angled triangle right here, the square root of, we're going to have the difference in the x values. So I can just write x2 minus x1 and square it, and add the difference between our y values, y2 minus y1, and square that. Which we figured out would be difference in our x values is -4 minus -1, which is -3, but we care about the length, so I have the absolute value. Even if you don't have the absolute value, you're squaring it anyway, so you'll be fine. So we have 3 squared, and then the difference here is 1, so plus 1 squared. That leaves us with 9 plus 1, which is the square root of 10. So the magnitude of this vector is the square root of 10. Okay, so I forgot to record part B, but I'll just go over it quickly. So part B says, determine the coordinates of point D on vector CD if C is this, so right here, at -6 and 0, and CD is an equal vector to AB. So for AB, since we went over 3 and up 1, CD should do the same thing because it's pointing in the same direction. So to calculate where we would go, we would start for our coordinates for D, we would start at C, so our x coordinate, and then add 3 over, and then our y coordinate at 0 and adding 1 up. And that'll give us our coordinates for D to be -3 and 1.